The next method of finding the time complexity of a code is to see how many elements of the given data structure are being modified inside the code. Sometimes loop does not give us the right picture and we have to see how many elements are getting modified to find the time complexity of the code. Consider this example. In this code, the condition of the while loop is while I is less than n. So while I is less than n gives an impression as if this loop is executing n times because I is starting from 0. But we have to see that I is not being incremented by 1. Inside the while loop, we don't have I is equal to I plus 1. Instead, I is incremented by the element at the current index, that is I. So if the array is 2, 1, 3, 1, 2, minus 1, then the first element is 2. So initially I is at 0. Therefore, I will be incremented by 2 and I will reach here. Now because the value at index I is 3, so it will jump 3 places and I will go directly here. The element at this index is minus 1, so I will go back one step. And then the index at this element is 2, so I will move outside the array and the loop will stop. Therefore, it is not guaranteed that this loop will execute exactly n number of times. It may get executed more than n number of times, or it may get executed less than n number of times, or it may become an infinite loop. We don't know. Therefore, if the array is not given to us, then the worst case time complexity is that it is an infinite loop. If we are given that all the elements in the array are positive, then we know that I cannot go backward. Therefore, in that case, the worst case time complexity will be order of n. But if negative elements are given, then I can move forward in one step and then backward again. Forward and backward can continue infinitely, and this will become an infinite loop. Therefore, on the one hand, we are still counting the iterations of the while loop, but on the other hand, because the number of iterations of the while loop depend on the elements of the array, so we have to consider the elements of the array. In some questions, you are given a linked list where every node has 2 pointers. One is the next pointer and second is a random pointer. So this pointer is the next pointer and this pointer is a random pointer, and this is obviously the data. If we are traversing the linked list using the random pointer, so instead of saying node is equal to node dot next, we say node is equal to node dot random pointer. Then the time complexity of this while loop may not necessarily be n. Consider this code related to graph. We know that graph is a collection of vertices and edges. In this code, we represent the total number of vertices and this adjacency array represents the information about the edges. The outer loop in this case runs v times, which means that the outer loop is executing for every vertex. And the inner loop, and for every vertex, the inner loop executes k times, where k is the number of adjacent vertices of u. And if that vertex is not visited, then we just mark it visited and process that vertex. So this is a typical piece of logic which is used in many graph algorithms. Now the outer loop executes v times, but how many times is the inner loop getting executed? In the worst case, the inner loop can execute v minus 1 times because every vertex can be adjacent to every other vertex in the graph. But what is the exact measure that you will put? So we will say that this code takes v plus e times, where v is the number of vertices and e is the total number of edges in the graph. Because the total number of times the inner for loop execute for all the iterations of the outer for loop will be e. That is the number of edges. Consider this code. This code takes two arrays A and B. Both of these arrays are sorted and the length of both of these arrays is n. This code uses the merging logic, which means that initially we have 2 pointers I and j, and both I and j are pointing to the first elements of each array respectively. If the corresponding 2 elements of the array are not equal, then we will either do I++ or we will do j++. But when the 2 elements are equal, then we increment the count and increment both I and j. At the end of this while loop, count will give us the total number of elements which are common in both the arrays. The best case running time of this algorithm comes when in every iteration of the while loop, we increment both I and j. And the worst case iteration will come when alternately I and j will be incremented. So this is a typical merging logic, and the time complexity of this code is big O of m plus n in the worst case. This code is again related to graphs, and we are trying to do the BFS traversal of a graph. BFS is the breadth first traversal of the graph, where we use Q data structure. So we are declaring this visited vector which will keep the information of all the visited nodes in the graph. Then we declare a Q that will be used for BFS. In the Q, first we will insert the source vertex of the graph, which is this SRC vertex. So q dot push src, and src is now visited, so visited of src will be true. So source comes here. If the graph is a b c d, then a comes here considering a is the source. Then comes this while loop. In the while loop, we will be removing one element from the queue and then inserting all the adjacent nodes of that vertex again in the queue. So first we remove from the front, which means that A will be removed. And then for all the vertices which are adjacent to A, all of those vertices will be inserted back into the queue only when they are not already visited. So A is removed and B will be inserted in the queue because A has only one adjacent vertex. Then B will be removed and the adjacent nodes of B are considered. A, C and D. All three nodes are adjacent to B, but since A is already visited, so only C and D will be inserted back into the queue. Let's come to the time complexity. You have an outer while loop and you have an inner for loop. So intuitively we can think that the time complexity will be n square. But here you have to look at it from a different angle. Every vertex is getting inserted in the queue only once. And inserting in the queue takes constant time. So for every vertex, we are taking constant time. So the total time taken for inserting and deleting from the queue is order of V. Now for every vertex, we are considering every edge. But every edge will be considered only once. If it is a undirected graph, then edge will be considered twice because undirected edge is considered from both the vertices. But if it is a directed graph, then one edge will be considered only once. So every edge is considered once. It means that the total time taken to consider all the edges is order of E, where E is the number of edges. So total time taken by this entire BFS algorithm is order of V plus E, where V is the number of vertices and E is the number of edges. Therefore, it will be easier to find the time complexity by considering the elements rather than focusing on the loops. Consider this function. This function cumulate. Let's assume that the array is 5, 3, 3, 2, 2, 2, 8, 6, 6. So what this function is supposed to do is that 5, because 5 is not repeating, 5 will remain here. Then because 3 is repeating, all the repeated values of 3 will be added to the first value. So it will become 3 plus 3, 6, and rest of the 3's will be 0. Similarly, all of these instances of 2 should be added to the first 2. So it will become 6, 2 plus 2 plus 2, and rest of the 2 will be 0. Because 8 is not repeating, so 8 will come as it is, and because 6 is repeating 2 times, so it will be 12 followed by 0. Now let's look at the algorithm. Initially I is 0. The outer loop is iterating while I is less than the length of the array. This is a Java code, so we are using nums.length. If it is a C++ code, then the length of the array must be a parameter in the function. Let's say I is here at 2. Now inside the while loop, we store this 2 in a temporary variable, and then we go to all the 2's after this 2. So this inner while loop will start from I plus 1 and it will keep on iterating as long as the value at j is equal to 2. So if temp is equal to element at j, then we add element at j to element at I. And if they are not equal, then we break from this while loop. So j comes here, then j comes here, and then j comes here. Now because 8 is not equal to 2, so we break from this loop. Now this code is taking n square time because the outer loop is incrementing one at a time. But if we adjust this so that I directly jump to j, I comes here directly, then every element of the array will be accessed only once. This is the optimized code, and this code is taking order of n time. In this code, every element is accessed only once. If that element is considered in the inner while loop, then the outer while loop does not reconsider the element again. We all know the famous pre-order traversal of the tree. If I ask you how much time does the pre-order traversal takes, you will say that pre-order traversal takes order of n time, where n is the total number of nodes. But this is a recursive code in which pre-order traversal is calling itself 2 times. So how are we finding this time complexity, and how are we coming to the conclusion that the time taken is order of n? We are coming to this conclusion because we are considering the number of elements. Because this function pre-order is getting called for every node only once. We will see the analysis of this function in more detail in the later sections, but you got the point. In some code, considering the loops may not give us the right answer, and it may mislead us to assume that the time complexity is order of n square or n cube, whereas the actual time complexity is either linear or something different from that conclusion. Therefore, in those situations, considering how many times is every element of the data structure being processed will give us the right picture.